This video focuses on a linear programming problem. It will be quite long problem. We will be doing this in class also, so I'm doing this more for students who are absent today. So our problem is a tourist agency can sell up to 1,200 travel packages for a Vikings football game that'll go to Seattle, Washington. The package includes airfare, weekend accommodations, and the choice of two different types of flights. A non-stop flight goes directly to Seattle, and a two-stop flight, so it has to stop 2 times before it gets to Seattle. The non-stop flight can carry up to 150 passengers, so think of your plane, 150 people can get into that plane. And the two-stop flight, so let's say a smaller plane, has 100 passengers. The agency can locate no more than 10 planes for the travel package, so think about 10 planes heading out to Seattle to go to this Vikings game. Each package with a non-stop flight sells for $600. And the two-stop is a little bit cheaper because it has more stops, is $400. Assume that each plane can carry the maximum number of passengers, a full flight. So step 1, we want to go ahead and identify the variables. So we want to identify the non-stop flights. So identify that in red here. That's your X. Then we have our two-stop flight. That's our y. So there are two variables, x and y. And then we can come up with our constraints, or our inequalities, within this word problem. This is probably the hardest part for students to understand. So one of the constraints is that the plane can only hold, for the nonstop, 150 people. And then the two-stop can hold 100 people. And there's no more than 1,200 people that can go on the flight. So there's our first inequality, is the inequality on people that get to travel to Seattle. The next thing is x plus y is less than or equal to 10. If you remember from this piece here in the green, no more than 10 flights. So there's so many of the non-stop and the two-stop, and it can't be any more than 10 planes heading out there. The last two constraints are x has to be greater than or equal to 0, y has to be greater than or equal to 0. What those mean is you can't have negative amounts of planes, nonstop flights. All right, let's move on to page 2. What we have to do is we have to go out and graph these 4 constraints. The 2 hardest ones are when we don't have them in slope-intercept form. So what we have to do is we have to convert these to slope-intercept form. So we're going to go ahead and solve this first inequality for y. So I'm going to subtract 150x from both sides. And I'm left with 100y on the left, less than or equal to 1,200 minus 150x. Then I have to divide both sides by 100. So I get y is less than or equal to 1,200 divided by 100 is 12. 150 divided by 100 is 1.5, or you could just reduce that by 10. So let's just say, let's divide this by 10, and that by 10, so you get 10 over 15. And reduce it again, I'm going to go by 5, so I get 3 halves. So the reduced fraction is 3 halves. So let's put this in slope-intercept form. Y is less than or equal to negative 3 halves, that's your slope, plus 12, which is your y-intercept. All right, let's head over to this green one, a little bit easier. So we're going to solve this for y. So we're going to subtract x from both sides and then put it into the correct order. So our slope is negative 1 and our y-intercept is 10. Now we're going to graph these. So one of the constraints was x has to be greater than or equal to 0 and y has to be greater than or equal to 0. So what that does is it eliminates the other quadrants and it focuses on quadrant 1 only. No negative numbers. Now we have to go back to this slide and graph these other 2 inequalities. So we're going to graph this one. Y equals negative 3 halves x plus 12. Then we're gonna go back, we're gonna graph this one, y equals negative x plus 10. All right, so let's go ahead and graph those. So again, we talked about these two that allows us to go into the first quadrant. Now I'll graph this one. So our y-intercept is 12. So go up 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there is our y-intercept, and we'll head down 3, and then over 2. We'll go down 3, and over 2. Down 3, and over 2. Down 3, and over 2. And now we create our solid line, and we read this inequality. It should be less than or equal to, excuse me here, less than or equal to. So what we're going to do is we're going to shade below in here. Well, I'm just going to remember that for now because it's going to get a little bit messier. So now let's go ahead and graph this one here. This one also should be less than or equal to. So let's fix that, less than or equal to. So we'll do our y-intercept. Our y-intercept is 10, and our slope is negative 1. So we're down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. All right, so now we have our last inequality graphed out, and what we notice here is also less than, so it's below. So now I'm just going to change colors here. I notice that I have to go and graph this region right in here, and this is what we call the feasible region. And we want to find in step 4 the 4 corners. So one of the corners is 0, 0. One of the other corners is 1, 2, 3, 4, 5, 6, 7, 8, 8, 0. This corner here is 0, 10. And this last one here is 1, 2, 3, 4. And then up 1, 2, 3, 4, 5, 6. Those are our 4 corners of the region. Now I need to write the equation that you want to maximize. So I already have this here. What I added is $600 times 150 people in a plane, and then however many planes you have. This is $400, 100 people on the plane, and then however many Y planes you have. That's your objective function. If you want to go back to this first slide, where I got that from again is $600, $400, 150 people, 100 people. And we want to find out the revenue. How much will the agency take in given the different scenarios for planes? So we're going to use this on the next slide. All right, I'm going to go ahead and stop there just so this movie doesn't get too long, and then we'll finish up step 6 and 7 on the next video. You're doing a great job.